Let's see here. Yeah. I will pray. So, Dear Father, we thank you for this day again. I thank you for this class. Just ask you to bless our time, help us to glorify what we do, and just understand the solution to the nth order problem today, Lord. In your name I pray, Lord Jesus. Amen. Was it ready? Thank you. So, I may have failed to say this anywhere, but like next time, oh no, I haven't. I don't want to pick on anyone in particular, but if you look at the stack, you'll notice that there are many fuzzy edges. These are fuzzy edges. Non-fuzzy edged papers. This is what I'm talking about. I don't want these on there because it makes a mess. But anyway, now you know. So you were like, what on earth are you talking about, fuzzy edges? I guess now we have, now you know. So, all right. Okay, let's talk about math. So our goal is to solve, we'd like to solve L of y equals to 0, where L is equal to, something like an d to the n plus a2d squared plus a1d plus a naught. And all these coefficients are real numbers with a sub n not equal to 0. All right? That's our goal here, is to solve this problem. Now, last time I told you the theory of the nth order problem, right? Which is that if the coefficient functions for the nth order problem are continuous, there exists a solution, right? And in fact, the general solution can be written as a linear combination of the fundamental solution set. So if we could find this fundamental solution set, we'd have solved the problem. So first of all, can we solve this problem? Like, are these coefficients continuous? Well, they're constants, right? All of the coefficient functions here are just constant functions. They're everywhere continuous. So the theory we talked about last time says, yeah, we can solve this everywhere. The question is how, all right? And so what I'm going to do is I'm going to build up to that solution in pieces. So I'm going to start out with a simple lemma. We'll call this lemma 1. Which is that if we look at d minus lambda acting on y equals to 0, that tells me that y is equal to, let's just say it this way. It says y equals e to the lambda x is solution. Now there's different ways we could just prove it simply by, working this out. Now this d here is what? In this context, I mean d is what? D is equal to the derivative operator. All right? Okay, so then, student's choice. Do you want me to derive this solution, or do you want me to just show you that it is a solution? Just show? All right. You gave me the easy way out. Here we go. So d minus lambda times e to the lambda x, what do we get? By definition, this is d of e to the lambda x minus lambda e to the lambda x. So here I'm using a definition of operators. Let me make a definition over here. Definition, if t1 and t2 are operators, then t1 plus t2 acting on a function is t1 of the function plus t2 of the function, also a constant times t1 acting on the function is equal to that constant times t1 acting on the function. So this is how we add the addition of operators is defined pointwise. All right? If we have a sum of two operators, or a scalar multiple of an operator, we simply act by these pointwise rules, right? So I'm using that definition there in the calculation I made over here for my lemma, all right? I'm using this definition, you notice, because d minus lambda, what is that? Well, that's d acting on e to the lambda x minus lambda acting on e to the lambda x. But what is this? Great. Well, this is d dx, right? Of e to the lambda x minus lambda e to the lambda x. But what is this? This is, by the chain rule, lambda e to the lambda x. And what do we got? We got 0. So apparently I was right. Okay? Now some of you might be like, well, but why is this true? Fine. For those of you who ask the question, why is this true? You're asking for a derivation, right? Why is the solution this? Well, if we take the operator equation, what we're up against is dy dx minus lambda y equals to 0, which if we separate, we got dy dx equals to lambda y, which we can separate and integrate, and that will tell us that y is equal to some constant times e to the lambda x by the usual separation of variables argument. So we can derive this claim simply by separation of variables, right? There's nothing mysterious about it. We should all have been able to find this, right? All I've done for lemma 1 is write a first order differential equation in a new notation, okay? You with me so far? So how about lemma 2? D minus lambda squared acting on y equals to 0 has solutions y1 equals e to the lambda x and y2 equals to x e to the lambda x. All right. Now it's easy enough to let's prove that I'm right, you know. Let's check it. So what happens here? What does d minus lambda squared mean, by the way? I guess I owe you a definition, right? T1 times T2 of f, what that means is T1 of T2 of f. Multiplication of operators corresponds to composition. When I write d minus lambda squared, what I'm saying, right, is the following. So let me add some parentheses in here to emphasize what's going on. So we're first operating by d minus lambda one time, and then we operate it by d minus lambda a second time. This is what d minus lambda squared means. So check it out. What happens if I put d minus lambda squared and I feed it e to the lambda x? What happens then? What's going on with the thing in the square brackets there that I'm about to underline in green? What is that? That's 0. That's 0. By lemma 1, right? This is 0. And guess what? While I have not assumed this yet over here, if T of CF plus G is equal to CTF plus T of G, then T is linear operator. Linear operator, if that's true for all functions. Here's the thing about a linear operator. What happens if you feed it 0 plus 0? What's T of like 0 plus 0? Think about this. What's T of 0 plus 0? It's T of 0 plus T of 0, right? If it's a linear operator. But what else is 0 plus 0? It's just what? If you allow me this small Menga style calculation, it's T of 0. So if we've got t of 0 is equal to t of 0 plus t of 0, what's it say about t of 0? T of 0 must be, think about it, anything that's equal to itself added to itself. It has to be 0, right. Subtract t of 0 from both sides, you get t of 0 equal to 0. So what that means is that a linear transformation is a transformation which sends 0 to 0. All right? Is d minus lambda a linear transformation? Is the derivative linear? It is. How about multiplication by a constant? Is that a linear transformation? It is. So because d minus lambda is a linear transformation, the fact that I'm feeding it 0 means that this is 0. Okay? How about the other thing? What about d minus lambda squared acting on x e to the lambda x? How's that go? Well, here I've got d minus lambda acting on the derivative with respect to x on x e to the lambda x minus lambda x e to the lambda x, right? So that's by the definition of the operation we're looking at. Okay, so what do I have to do on the thing I'm about to underline in this hideous Carolina blue? It's kind of Carolina blue. I'm not sure. What is this? I don't know what this is. What is it? Cyan. Oh, I guess. I think that's right. That's a product, right? So I have to do the product rule. And what does that give us? That gives us e to the lambda x, right? Plus lambda x e to the lambda x by the chain rule. And we still got this minus lambda x e to the lambda x over here. So what happens? These guys, they be canceling, right? And then what are you left with? E to lambda x. What is that? What happens when we hit d minus lambda on that?
0.
At 0. So this is 0. So apparently, d minus lambda squared has solutions e to lambda x and x e to lambda x. By the way, those are linearly independent. We proved that in the other class, right? These are linearly independent solutions. Okay, so at this point, I feel like I owe you a general comment, observation, we could say. Observation. If, let's say, p of x, maybe x is the wrong thing. Let me say p of t. Fine, yeah, p of t is equal to, let's say, an t to the n plus, let me not use a's, I'll use b's. bn t to the n plus dot 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 plus like b2 t squared plus b1 t plus b naught. All right, so what is that? What did I just write there? What is that called? What kind of formula is that? Is it a sine? Is it exponential? Is it a rational function? What are we looking at here? It's what? I didn't hear you.
It's a series.
A series. Ooh, too greedy, too greedy. I mean, I guess you could say it's a series. It's a series with infinitely many terms which are 0, right? But no, this is a polynomial, right? This is an nth order polynomial. Yeah? Polynomial. Then we define, all right, p of the differentiation operator, like b and d to the power n plus dot 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 plus b2 d squared plus b1 times the differentiator operator plus b0. So if we have a polynomial, we can define a corresponding polynomial of the differentiation operator. All right? Here's the cool thing. This is a linear transformation. Why is that? The reason is that the differentiation operator is linear, the second differentiation operator is linear, the third derivative is linear, the nth derivative is linear, all of these are linear, and multiplication by a constant, that's linear as well. If you multiply a linear transformation by a constant, you still get a linear transformation. And guess what else? The sum of linear transformations is again a linear transformation. So you put this all together, and we have this wonderful result that any polynomial in the differentiation operator is linear. All right? So we were just using a specific example of that in my lemma 2, right? I'm claiming that d minus lambda squared and d minus lambda are linear, right? It's like, for example, just to illustrate this notation, so if I have like p of t is t minus lambda, or if I have p of t is t minus lambda squared, which by the way is t squared minus 2t lambda plus lambda squared, right? Then see if I can find a better marker. Then, like p of d is d minus lambda. And the second one, let me call this p1, p2. p2 of d is actually d squared minus 2d lambda plus lambda squared. But what's actually really neat about all this, and I'll show you an example of this before I'm going to make a general claim, and then rather than proving the general claim, which you would all like fall asleep, all right, if I did prove this claim in general. But it is true, you notice something here. This is also equal to d minus lambda squared. What I'm saying is that polynomial algebra and the idea of putting an operator into the polynomial, these two things are interchangeable. Let me write it as a theorem. Theorem. If we have like g of t is equal to, say, f1 of t times f2 of t, all right, where f1 and f2 are polynomials. All right, then g of the differentiation operator is actually equal to f1 of the differentiation operator composed with f2 of the differentiation operator. See this multiplication here, multiplication of operators corresponds to composition of operators. Let me put this in more simple terms for you. We can do polynomial algebra for polynomials in the differentiation operator. Let me show you an example where we work this out explicitly for something that's a little bit more concrete. All right. So, like example 2, we could look at, say, f1 of t is like t minus 2, and f2 of t is, say, t plus 3, let's say. Okay. So what happens when you multiply these? What's f1 times f2 of t here? T squared plus t minus 6. That sounds right. So in the language of my theorem, we have g of t so I heard a t squared plus t minus 6. Great. All right. So if we look at g of the differentiation operator, what is that? That's second derivative plus the derivative minus 6. Okay? So if we let this act on a function, all right, then that gives us d squared f plus df minus 6f, which in prime notation maybe makes it more concrete for you guys. I don't know. F prime prime plus f prime minus 6, okay? 6f. That's what we get from g of d acting on the function, right? Let's contrast that to what happens if we have f1 of d composed with f2 of d. Like, let's try this out. So what if we have f1 of d times f2 of d acting on a function? Well, that is f1 of d, right, acting on f2 of d acting on the function. By definition, the multiplication of two operators is composition of the operators, all right? So specifically here, for my example, this is, let's see here, d plus 3, and we're feeding it d minus 2 acting on the function, all right? How does that go? Well, we've got d plus 3, and it's being fed, this is what? This is f prime minus 2f, right? You guys with me so far? Then what? Then we let d plus 3 do its work on that, right? What goes on there? Let's see here. So, this is, by definition, this is d times f prime minus 2f plus 3 times f prime minus 2f.
For f1 and f2. Just like, f1 is t minus 2, and you have this plus 3.
Did I flip them? Oh, here, I'll fix it. Thank you. We good? Yeah. Okay. So then what happens is we've got what? We've got f prime prime minus 2f prime, well, 2f prime plus 3f prime minus 6 times f. But what is this? This is f prime prime plus f prime minus 6f, right? Which, of course, is equal to g of d acting on f, right? And by the way, we could have done the same calculation that I claimed we were doing at the outset, right? This would also be what we would get if we were to try f1 of d times f2 of d, acting on f2 of d acting on f. Now, some of you might be like, wait a minute, where's the f coming from? Like, I thought we're talking about g of d and we're talking about f1 of d, talking about f2 of t. Like, where's this f coming from? What is this f? F is a test function. And here's the general principle, definition. Two operators, let's say t1 and t2, are equal if and only if t1 acting on f is equal to t2 acting on f for all appropriate test functions. Now, I threw that weasel word in there for you, appropriate, because different operators have different contexts, right? If we're talking about differential operators, surely we don't want to look at functions which can't be differentiated, right? So for our current context, we should probably limit the scope to smooth functions, right? Functions which we can differentiate as many times as we like. If we can prove these identities hold for smooth functions, then it proves that these are equal operators in the realm of smooth functions. So the thing is, just to try to stick a fork in it here, we have this is equal to, that for all f. This holds for all test functions f. So therefore, our conclusion from that data is that f2 of d times f1 of d is actually equal to g of d. So this is an operator equation. I'm saying that those two operators are equal. So this is probably new for you, right? This idea of an operator. An operator is what? It's a function of functions. An operator takes in a function and it spits back out a function. Now you've been working with operators all along, right? The derivative is an operator. You give it a function and it outputs a function, right? But we're just taking another step of abstraction here and saying that we can think about the collective action of like higher derivatives and linear combinations of those all together as one transformation, one linear operator, and we can study its structure. That's what we're doing today. And once we understand that structure, we will have solved this problem entirely, all right? And that's going to happen in the next about 30 minutes. Okay, so next step in the thing is, okay, so at this point I kind of needed to chase a rabbit for a second and show you that this fact that polynomials in the differentiation operator, this theorem is special, all right? This theorem is very special. The fact that you can just simply multiply the polynomials using polynomial algebra and the same will be true. You understand the difference here. Understand the difference of the theorem. On the top, I'm talking about multiplying polynomials, right? On the bottom, I'm talking about composing transformations, right? Those are really different things. I hope you just see that in the example we just did. The difference between multiplication and composition. They're really different. So the fact that we can simply multiply polynomials and then, we could either stick the differentiation operator before or after and then multiply them. Like this freedom we have to do polynomial algebra in polynomials of the differentiation operator is special. If we look at operators that are not just this, if we look at operators that have coefficients which are not constants, things don't work out so nice. I need to show you an example of that so you appreciate the specialness of what we're doing. So example 3, if we have, say, t is equal to the differentiation operator, and if we have, say, s is equal to x times the differentiation operator. This is not something that was allowed. The multiplications we've had up to this point are only multiplications by a number, a constant number, not x. There's no variable here. Let's see what happens when we hit this with a test function. Ts acting on f. What's that give you? Right? So sometimes I put like parentheses and square brackets to indicate operation on function. So I'll do that here. So we have t s of f. All right, great. What does that mean here? That means d dx acting on x times df dx. But what is that? That's a product of functions. So I have to do the product rule. So I have df dx plus x times, well, what? D squared f, dx squared, right? Or if you want me to, well, whether or not you want me to, I'm going to, we could rewrite this as d plus x d squared acting on f. All right? So this calculation here shows you that Ts is actually equal to what? Ts is the differentiation operator plus x times the square of the differentiation operator. All right? Now, what if I go the other way? What if I instead calculate St acting on f? What happens then? How is that different? Right. So this time the x times d dx comes second, and the differentiation comes first, right? Composition, the order matters, right? There's an inside and an outside for composition. F composed with G is not the same as G composed with F. So composition of operators, the order matters. And of course what you have here is x times d squared acting on F. So apparently S times T as an operator equation is simply equal to xd squared. They're not equal, right? I can't just do polynomial algebra here, and like polynomial algebra, among other things, is commutative, right? So I made a mistake. I switched the order of 1 and 2 in example 2, right? This was pointed out to me mid-example, but it didn't matter because f1 times f2 is equal to f2 times f1 because it's polynomial algebra. When you're not dealing with a polynomial of an operator, as we're not here, like s is not a polynomial in the differentiation operator, the order matters. Like I can't just commute operators. However, I can commute polynomials in the differentiation operator. That's special. Now here there's something interesting to think about. There's something called the commutator. You're like, what's that? Well, the commutator of t and s is equal to ts minus st. And from the calculations we just did, what's the commutator? So ts minus st is what? Yeah, d. So the differentiation operator is equal to the commutator of t and s. If you study quantum mechanics, the commutator of operators plays a special role. It turns out if you want to simultaneously observe two physical variables, you need that their commutator is 0. Otherwise, you can't simultaneously measure them in the same eigenstate. So the theory of linear algebra says, like, in order to simultaneously diagonalize two operators, they must have a commutator which is 0. So this plays a large role in like how we assign quantum numbers and things like this. If you go on and take the quantum mechanics class, which I might be teaching next spring, maybe. I don't know. We'll see. I hope. We're supposed to start teaching residential physics classes like next year. I mean, we've already had the modern physics class going, but we're supposed to have like mechanics, E&M, and quantum running next year residentially. So I'm slated to teach E&M in the fall and then quantum mechanics in the spring. And I think Dr. Budar is going to teach mechanics in the fall, if all goes as we hope. So, and I think he teaches modern in the spring, modern physics. Those are all available as technical electives. Okay, end of advertisement. All right, anyway, let's go on here. So we got our lemma 1, we got our lemma 2. I'm going to erase and go forward here. Uh-oh. Okay. Phew. It's like, did I move the camera? Sad. All right. So think about this. Lemma 3. We'll continue with this story. D minus lambda to the k acting on y equals to 0 has solutions y1 equals e to the lambda x, y2 equals to x e to the lambda x, and so forth and so on. Eventually we get y sub k equals x to the k minus 1 e to the lambda x. All right. So I'm going to give you a proof by induction. All right. So it's true for k equals to 1, right? That's lemma 1. Yeah? Suppose it's true for suppose it's true for k, and then we'll consider k plus 1, all right? So if we look at k plus 1, d minus lambda to the k plus 1, right, acting on y equals to 0 is what? Well, that's equal to what? D minus lambda times d minus lambda to the k, right? What do we have by the induction hypothesis here? So this is 0 for y1 equals to e to the lambda x, y2 equals x e to the lambda x, all the way on out to yk equals x to the k minus 1 e to the lambda x by the induction hypothesis. Right. I think you guys study induction in Math 250 if you've had it, right? If you haven't seen induction before, I'm sorry, but it'll still be over soon. So in induction, we assume it's true for k, and we try to prove it's true for k plus 1. If we can do that for arbitrary k, then we've established that the claim is true for all integers, assuming we've already established the base case, which we have. Now, do you see why this is true? Now, so if by assumption of the induction hypothesis, this has solutions as listed, right? Which makes this be 0. But if this is 0, I feed it to the d minus lambda, we still get 0. So that's why all of those work. So all that remains is to, so what does it remain? It just remains to do what? It remains to check yk plus 1 equals to x to the k e to the lambda x, right? So we do that, d minus lambda to the k plus 1, and we'll let that act on x to the k e to the lambda x. But by definition, that's d minus lambda to the k acting on d minus lambda times x to the power k e to lambda x. I'll get out of the way here in a second, guys. So this time I'm going to put the k-fold one out front like that, all right? What happens when we, let me underline it in blue here. So we do this, right? What's that give us? That gives us d minus lambda to the power k. I differentiate. What do I get? I get k, x to the k minus 1, e to the lambda x, plus lambda, x to the k, e to the lambda x. That's the product rule of the differentiation operator acting on that, right? Then I still have what? Multiplication by lambda. So what happens here? As usual, stuff be canceling, right? Only the finest grammar for my classes. I will say this, if Trump actually destroys the Department of Education, we are going to have a party in here. There will be a literal party in my classes.
Really?
It will be, yes, it will be, there will be a party. And since the Liberty Way is very vague now, okay, I better not finish that sentence, but it will contribute to your human flourishing. We're all about flourishing now. Let's see here. So, what we got? What do you know about that? We already know that is 0 by the induction hypothesis, because that is the kth solution times the number, times k. So we already know that that's 0 by the induction hypothesis. So this is equal to 0, and through the magic of induction, we now have a solution to the case that we have a k-fold repeated root. So in the past, I sometimes just do the lemma again, but for like third order. If this leaves you unimpressed, just work the lemma out for order 3. And once you see that, you should become bored with it and believe that it's true for arbitrary order, all right? By the way, lemma 4, I won't prove this. Lemma 4, y1, my bad, e to the lambda x, x e to the lambda x, x to the k minus 1, e to the lambda x is linearly independent on R. All right. I mean, it's a straightforward calculation. You could calculate the Wronskian of these. It's clearly non-zero, right? These are linearly independent, all right? So what's next? Lemma 5, I guess. If L is equal to L1, L2, L sub r, and L1, L2, Lr are all linear transformations, which commute. So by commute, I mean that L1, let me just put it, commute, what I mean by that is like Li times Lj is equal to Lj times Li for all I and j. Like the commutative property. For example, the thing we're primarily interested in is just polynomials of the differentiation operator. Those commute, all right? That's the application we have in mind here. And if there exists, let's say, J such that L sub j of y equals to 0 for some y, some function y, then here's the kicker, L of y is equal to 0. This is a huge one. This lemma is huge. What it says is that if we're trying to find things that are 0 when we have this composition of R operators. If we can make any one of these in this list of commuting operators sent to 0 with the function, we send them all to 0. So in other words, this is the divide and conquer lemma. It says to solve L of y equals to 0, it suffices to separately solve L of 1 y equals to 0, L2 of y equals to 0, and down on the line. If I can find the solutions to each of the factors forming L, then I found the solution for L of y equals to 0. I sometimes call this the divide and conquer lemma. The proof is just kind of dumb. I'm not even going to write the proof out. The proof is pretty much obvious. Like, because you have L of j is y equals 0, when you feed it into the big L, because the operators commute, you can just move j so that it hits it first. Then it's 0, but these are all linear operators, so the rest of them just keep sending 0 to 0 to 0 to 0 to 0 to 0. So there's that. All right. You're like, please, sir, may I have another lemma? I'm glad you asked. Yes, I have more lemmas. I got some more lemmas. When life gives you lemmas, yeah. That's horrible. But I'll allow it. Lemma 6. If L is a real, smooth differential operator, and L of y1 equals to f1 and L of y2 equals to f2, all right, then L of y1 plus y2 is equal to f1 plus f2. In fact, I don't think this is just an if-then. This is actually, well, yeah, fine. I'll give it an if-then format. What I'm trying to say is, let me put this into words. A complex solution gives two real solutions. for a real differential equation. All right. Now you might be like, well, why are you talking about that? Where'd that come from, right? Well, I've been doing it all along, I just didn't tell you. What is e to the lambda x? What does that mean? Did I say that lambda was real? Search your heart. Find that I was silent on this point. I just started saying lambda. I never told you where it was. The answer is, it's a complex number. It just so happens that the derivative of e to the complex lambda times x is still equal to lambda e to the lambda x. So I probably owe you a little discussion of that, right? So here's the thing. If I have e to the alpha plus I beta times t, or let's say x, I've been using x today. Well, that's equal to e to the alpha x times e to the I beta x, which by definition is e to the alpha x cosine beta x plus I e to the alpha x sine beta x. So, in other words, e to the lambda x is equal to this if I have lambda equals to alpha plus I beta. How do we differentiate a complex valued function of a real variable? Like, what's the definition? I mean, I'm going to work this out for you guys. ddx of e to the lambda x, how's it go? So by definition, this is ddx of e to the alpha x cosine beta x plus I times ddx e to the alpha x sine beta x. So this up here, this is a definition. This is a definition. Down here, this is also a definition at the moment. This is the definition of differentiation of a complex valued function of a real variable. If you think back to the hint I gave you guys about the isogonal problem, where I was talking about how we can look at complex numbers as vectors, all I'm really saying is that if you're going to differentiate a vector valued function of x, you differentiate the real part with respect to x, and you differentiate the imaginary part with respect to x, which is the same thing we do in calculus 3 in a slightly different notation. You know, if I've got ddt of the vector xy, by definition, you know, the x dt comma dy dt, that's how we differentiate, right? That's all I'm doing here. I'm just doing it in a complex notation. All right? But what happens when we differentiate a product of functions? We get product rule, right? So this is alpha e to the alpha x cos beta x minus beta e to the alpha x sine beta x plus I times alpha e to the alpha x sine beta x plus beta e to the alpha x cosine beta x. So I got product rule times 2. I can factor an alpha out. I got alpha times e to the alpha x cos beta x plus e to the alpha plus I e to the alpha x sine beta x. And then I'm going to factor out an I beta. I beta, well, I've got an e to the alpha x cosine beta x. And for the other term, that term with a minus, we need to use our imagination. Pun intended. So minus 1 is I squared. Delayed reaction, the best. So minus 1 is I squared. So if I trade that minus for an I times I pull one I out here, and I put the other one in here. So, but what do we have? What are we looking at? This is e to the lambda x. This is e to the lambda x. Therefore, we have alpha plus I beta by factoring e to the lambda x, also known as lambda e to the lambda x. All of the steps and the lemmas I made equally well apply to calculus of a complex valued function of a real variable. So everything I've said up to now equally well applies in the case that lambda is complex. So we either could have lambdas real or we could have lambdas complex. Either way, we've got our lemmas. But the cool thing is, if lambda is complex, we get not just one solution, but two solutions from e to the lambda x. And likewise from x e to the lambda x. All right. You guys ready to solve some differential equations? Let's do it. I think we have everything we need. Put it together. Our goal, our mission, should you choose to accept it, is to find n linearly independent solutions to each differential equation of order n. The method is simply this. Write down the polynomial which defines the differential equation. Factor said polynomial. Write solutions down from the lemmas. In the case that they have a complex factor, we have to separate into the real and imaginary parts. But I'll illustrate that by example rather than by besieging you with an additional. I could probably make another 4 lemmas here to make it abstract, but I think at this point, you've indulged me long enough. I owe you some examples. So let's do it. So where am I? Example 3? Is that right? I think. All right. Here we go. Solve. Y prime prime minus 2y prime plus y equals to 0. Here's my thought process. I go, as an operator equation, this is d squared minus 2d plus 1. Acting on y equals to 0, which is d minus 1 squared. Acting on y equals to 0. Therefore, by the theory last class and by lemma 2 today, the solution is simply y equals c1 e to the x plus c2 x e to the x. Done. That's the general solution. It's second order. I just built a solution with 2 linearly independent, functions. To connect with the lemmas, what's my lambda equal to here? I just had what? Lambda equals to? Lambda equals to 1. All right? Shall we do another? Let's try another. What if I was up against, I don't know, y prime prime 3 primes plus 5y prime prime plus, let us say, 6y prime equals to 0. So I rewrite this as an operator equation, d cubed plus 6d, right? So I've got that acting on y equals to 0. Can you guys tell me how to factor that? Pull out a d, yeah. Oh yeah, d plus what? D plus 3, yeah. So what I'm doing, guys, now is I'm just the thought process is I'm thinking of this as like L1. I'm thinking of this as like an L2. I'm thinking of this as like L3 in my lemma, right? If I can solve any one of those, if I can find a function that makes any one of those go to 0 upon operation, the whole thing goes to 0. But it's easy to solve each one of those separately, right? Lambda equals to 0, lambda equals to minus 2, lambda equals to minus 3. Therefore, solution, C1, what's e to the 0x? Just e to the 0x is just 1. So I get C1 plus C2 e to the minus 2x plus C3 e to the minus 3x. As a general point of order, when we're solving the nth order homogeneous equation, we have to have a solution which is formed by n linearly independent functions, and there should appear Unless initial conditions are given, you should have constants C1 through Cn in the problem. Yeah? All right. How about this? Example 5. I've got y to the nth derivative acting on x equals to 0. This is d to the power n acting on y equals to 0. What's my solution? I don't know if you guys remember or not, we solved this before. At the start of this discussion, I integrated n times, right? And then upon your request, I relabeled the constants so it looked prettier. We're back there again. Solution is c1 plus c2x plus c3x squared plus dot 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 plus cn x to the n minus 1. So here we have lambda equals to 0 n-fold repeated. So that's your solution. Yeah? 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 Yeah.
For example, it was y to the n minus 3.
Y to the n minus 3, then that would be, that would be awkward. I would go all the way to c n minus 3, and this would be an n minus 2? 4. Minus 4. I can't do math.
But you would just continue it from the c n x to the n minus 1. You would just, so you would go like on top of that plus c.
Like for instance, if I was solving y prime 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 equals to 0, the solution is c1 plus c2x plus c2x squared, right? I don't know if that helps, but okay, let's do a complex one, yeah? So example 6. What if we're up against, say, the fourth derivative minus, we'll make it relatively easy, 81y equals to 0. So what's the polynomial problem I'm up against? I'm up against d to the fourth minus 81. What's that equal to? I heard a d squared plus 9 times d squared minus 9, right? I think maybe I owe you guys one more lemma. I'm starting to feel bad about not putting one more lemma in. I'll get in a second here, though. So this is d squared plus 9 times d plus 3 times d minus 3, right? Okay, so I guess I'll do it this way at the moment since I don't have my lemma yet. D squared plus 9 I can factor as d plus 3i times d minus 3i. All right. So I'm just going to kind of show you what goes on here. So this gives us lambda equals to minus 3i, right? And what's e to the minus 3ix equal to? Well, that's equal to c cosine of minus 3x plus I times the sine of minus 3x. In other words, since cosine's even and sine is odd, you get cosine of 3x minus I times the sine of 3x, okay? That would be that function when you evaluate on d plus 3i, that's 0, that complex function. On the other hand, d minus 3i, I've got lambda equals to 3i, right? So there we'd be looking at like e to the 3ix, which is cosine 3x plus I times the sine of 3.